dear students. I am Sunira from Department of Physics, Government College, Madappalli. In this lecture, we will learn about binary arithmetic. In our previous classes, we learned about binary numbers and floating point representation. Now, we have to check how to do binary arithmetic. So, we have certain assumptions. The first one is, these arithmetic operations are performed using registers. Okay? So, usually binary arithmetic is performed using registers. We assume 8-bit registers. We assume 8-bit registers. So, we discuss here binary arithmetic using 8-bit binary numbers. Okay, so we assume here our microprocessor or microcomputer perform its mathematical or arithmetic operations using 8-bit registers. Okay, the next assumption, this is the first assumption. The second assumption is the numbers represent using 2's complement form. 2's complement representation. Okay, so there are two assumptions. First one is binary arithmetic operations are performed in 8-bit registers. The second assumption is our numbers represent using 2's complement form. We already studied about 1's complement and 2's complement. These are the main two assumptions. Okay, now in our 8-bit registers, the leftmost bit is called as the sign bit. We already learned about it. So, suppose there are 8 bits like this. In these 8 bits, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so there are 8 bits. In these 8 bits, this leftmost bit is called sign bit. Sign bit. We already learned it. So, in this sign bit decide whether this number is positive or negative. The remaining 7 bits used to represent the magnitude of the number. So, in our binary number, we use 8-bit registers. The leftmost bit is used for sign bit, which decides positive or negative number, sign bit. The remaining 7 bits used to represent the magnitude of the binary number. Okay, now as all of you know, in the binary number system, we have two symbols. What are they? Yes, they are zeros and ones. So, in binary system, we have two symbols. They are 0 and 1. 0 and 1. So, we have to know the rules related with adding these two numbers, zeros and ones. Okay, so I am using a column and row to represent the rules of binary addition. So there are two numbers, the two symbols 0 and 1. Now to represent addition, I put here a plus symbol. In this way I am writing here the 0 and 1 again. Okay, in this table we can write the rules. So 0 plus 0 gives us 0, 0 here. Then 0 plus 1 gives us 1, so 1 here. Next, coming to the second row, 1 plus 0, 1 here. Then 1 plus 1, 1 plus 1, we know that it is 2, but in the binary system it is written like this, 1, 0. This is 2. So this one is called a carry. Okay, so in this 1 plus 1 gives you 1, 0, in which 1 is called as carry. 0 with carry 1. 1 plus 1 gives 0 with carry 1. These are the rules for adding two binary bits. Okay, adding binary bits. So we can, using these rules, we can represent, we can do the addition of two binary numbers. So we can move on to doing problems in connection with this binary addition. Now, okay, we can add binary equivalents of 8 and 7. Example 1 is add binary equivalents of 8 and 7. Okay, so we already learned how to convert a decimal number to its equivalent binary number. So now we want to write binary of 8. So 8 base 10, because this is decimal system 8. This is equivalent to 8. How to write 8? 8 means 2 cube. So 1, 0, 0. This is 8. But we already assumed that our register is 8-bit register. So we have to fill 8 bits. How to fill? So we have to write zeros here. That means 0, 0, 0. How many zeros? 4 zeros. Then 1, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits are there. This represents binary 8. Binary 8. So decimal 8 is equivalent to this binary number. Similarly, we have to write 7. 7 in decimal system. How to write 7? 4 plus 2 plus 1. So last 3 bits. 1, 2, 3, 4, 5, 6, 7, 8. 1 plus 2 plus 4, 7. Okay, so the binary representation, 8-bit representation of 7 is like this, and the 8-bit representation of 8 is like this. Now we want to add these two numbers. Okay, so we can add these two numbers here. So 0, 0, 0, 0, 1, 0, 0, 0 plus 0, 0, 0, 0, 0, 1, 1, 1. Okay. Now we can apply our binary rule. 0 plus 1, 1. 0 plus 1, 1. 0 plus 1, 1. 1 plus 0, 1. All others 0 plus 0, 0, 0, 0. This is our binary equivalent output. What is its decimal value? 1 plus 2, 3, 3 plus 4, 7, 7 plus 8, 15. Right? So this is equivalent to decimal 15. Okay? That means 8 plus 7. 8 plus 7, 15. We all know that. But now we want to check it using binary addition. So we use 8-bit registers to add these numbers. By adding these numbers, you get output like this. This is equivalent to decimal number 15. Okay? So I think that you understand how to add two binary numbers. Now we can add the second example by add 8 and minus 2. The first problem we add two positive numbers. The second example we add 8 and minus 2. Okay, so binary representation of 8 is already known. Last problem we done it. So we can write here 0 0 0 0 1 0 0 0. This is 8, binary equivalent of 8. Now we want to write its minus 2. How to write minus 2? Already we assume that we use 2's complement representation. So we have to represent minus 2 in 2's complement representation. So what we want to do? We have to write binary of 2, positive 2 first. Then we have to take its 1's complement. Then add 1 to it. Then you will get its 2's complement form. This 2's complement is called minus 2. Okay, so we can write first how to write minus 2 in binary form. This is 8, we already see that. So binary, this is equivalent to 18 decimal system. Now move on to 2. So 0 0 0 0 0 0 1 0. Okay, this is equal to 2 in decimal system, but we want minus 2, not 2. First we write 2 here, then we want to take its 1's complement. How to take 1's complement? By converting all zeros to 1 and 1's to 0, we get 1's complement. So 1's complement of 1's complement of 2. By converting this, you get 1 1 1 1 1 1 1 0 1. Okay, 1 2 3 4 5 6 7 8. 8 bits are here. The 6 bits, the leftmost 6 bits are ones. Next one goes to 0. The last 0 again becomes 1. This is the 1's complement of 2. Now we need 2's complement. How to write 2's complement? Choose complement. Add 1's complement plus 1 gives 2's complement. So we want to add 1 to this number. Okay, so this gives you 1 1 1 1 1 1 0 1 plus 0 0 0 0 0 0 1 0 1. Okay, 8-bit 1. So by adding this gives you 1 1 0 1 plus 1 0 with carry 1. Carry moves on to here. 0 plus 0 0 0 plus 1 carry 1 here. 1 plus 0 1 1 plus 0 1 1 plus 0 1 1 1 1. Okay, so we get this is as the 2's complement of 2. 2's complement of 2. Okay, so 2's complement of 2 is called as minus 2. So we can write minus 2 here. Minus 2 in decimal system So we get minus 2. Now we have binary representation of 8 and binary representation of minus 2. Now we have to add these two numbers. So 0, 0, 0, 0, 1, 0, 0, 0 plus. What is this? This is 8. Okay. Then minus 2. 1, 1, 1, 1, 1, 1, 1, 0. Okay. So 8 plus minus 2. Now adding this 0 plus 0, 0, 0 plus 1, 1, 0 plus 1, 1, 1 plus 1, yes 1 plus 1 is 0 with carry 1, carry move here, 1 plus 0 plus 1, again 0 with carry 1, 1 plus 0 plus 1, again 0 with carry 1, 0 plus 1 plus 1, again 0 with carry 1, 1 plus 0 plus 1, again 0 with carry 1. Okay, so we get result like this. The last bit is outside this 8-bit representation. You can see here 1, 2, 3, 4, 5, 6, 7, 8. The 9th bit is the last carry 1. This is called lost carry. This one is called lost carry. Why this is called lost carry? Because our register has only 8-bit capacity. 8-bit capacity. But here our addition gives 9-bit result. So the last bit is lost one. So it is called lost carry. But still you get the correct result. What is 8 plus minus 2? 8 plus minus 2? 8 plus minus 2 equal to 6. Right? Now you can convert this number. Without this carry, you can convert this number to a decimal system. See? What is its decimal equivalent? That means 0, 0, 0, 0, 0, 1, 1, 0. This is the binary number. Its decimal equivalent is 2 plus 4, 6. Right? Okay? So, I think you understand how to do this. In this case, you can see that by adding these two numbers, you have a extra bit, extra carry. This carry is called lost carry because of the capacity of the register. We assumed the capacity of register as 8-bit registers. Okay, so this one is lost carry. Due to this lost carry, you get the correct answer. Because of this lost carry, you get the correct answer 6. If you keep it here, you will not get the right answer, right? So, without this one, this lost carry, you get the correct result 6. Okay? Now, we can do another example using two negative numbers. As the third example, we will add minus 3 and minus 2. Add binary equivalence of minus 3 and minus 2. So, in this third problem, we add two negative numbers. So, we have to represent this in equivalent binary. Now, all of you understand and all of you know how to write minus 3. How to write minus 3 in 2's complement form? You have to write 3 first, then take its 1's complement, then add 1 to this complement form. You will get its 2's complement. Once you complete all these things, I just write here 0, 0, 0, 0, 0, 0, 1, 1. This is 3. This is equivalent to decimal 3. Okay. Now you have to take its 1's complement and add 1 to this. This gives you 0, 1. This is equivalent to minus 3. Okay. Now we want to add minus 2. In our last second problem, we did this one. How to represent minus 2 in binary. So I can write here binary minus 2 directly. 1, 1, 1, 1, 1, 1, 1, 0 in binary is equivalent to minus 2 in decimal system. Okay. Now we want to add these two numbers. So we can add these two numbers here. So 1, 1, 1, 1, 1, 1, 0, 1, 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Okay. This plus the next number minus 2. 1, 1, 1, 1, 1, 1, 1, 0. This is the minus 2. We want to add these two. So using the binary addition rules, 1 plus 0, 1, then 0 plus 1, 1, 1 plus 1, 0 with carry 1, carry 1 is here, carry 1 here. Okay, so 1 plus 1, 0 plus 1, 1 with carry 1. So here also carry 1 plus 1, 0, 0 plus 1, 1 with carry 1. 1 plus 1, 0 plus 1, 1 with carry 1. 1 plus 1, 0 with 0 plus 1 with carry 1. 1 plus 1, 0 with carry 1. Okay, so this is your output. Here also we have a lost carry. Okay, lost carry. What is this number? Except this lost carry, you have to get this number as minus 5 in decimal system. How to confirm this? To confirm this, you have to subtract 1 from here first. Then take its 1's complement. Then you get here the minus 5 equivalent representation. Okay, so this is the minus 5 in binary form. So you get this output as, by adding this minus 3 and minus 2 as 1, 1, 1, 1, 1, 0, 1, 1 as minus 5 in this decimal system. So in this case, the binary addition, we have done 3 examples. The first one is addition of 2 positive numbers. The second one is addition of a positive number with a negative number. The third one is addition of 2 negative numbers. In all these cases, we assume 2's complement representation. So taking the 2's complement of a positive number gives us the negative, its equivalent negative number. Using that, you can do all the arithmetic here, addition here, and find out the solutions. In these all additions, you can see that except the first one, the first example there is no carry. When it comes to the second and third example, you can see that there are extra carry, extra bit after the 8 bits of the memory. The last bit leads to the correct result of the addition. You can see from this. If this bit is here, the result is not correct. So, in all these problems, the lost carry gives you the correct result. Hope that you can do now binary arithmetic as you were on. Now, we can perform binary subtraction. Suppose we have 2 binary numbers A and B and want to find out A minus B. Okay, A and B are 2 binary numbers. We want to find out A minus B. So here we have to perform addition again, but this time using the 2's complement of the number being subtracted. That means here the number being subtracted is b. Okay, so we have to take 2's complement of b and add this number to the original number. This gives us the subtracted result of a minus b. So we can write here the 2's complement. 2's complement of b. Let it be c. 2's complement of b. Let it be c. Then a minus b is equal to a plus c. This is the rule for doing binary subtraction. So, if you want to subtract one number from another, you have to take 2's complement of the number being subtracted and want to add this to the first number. In this case, a is the first number, b is the number being subtracted. So, we want to take 2's complement of b, then add this 2's complement of b to the number a. This gives us the subtracted result. Okay, so there are 2 steps for performing binary subtraction. What are they? The first one is identify the number being subtracted and take its 2's complement. In this example, it is b. So, take this 2's complement. Then the second step is add this 2's complement to the number a, the first number. This gives you the subtracted result. Okay, now we can do problems using this principle. Okay, so example 1. The first one is subtract binary equivalence of 5 from 8. This is the problem. So we have to find out 8 minus 5. We all know the result, right? In decimal system, 8 minus 5 equal to 3. But we have to perform it using our binary numbers, just like microprocessors or microcomputers do. Okay, so to perform this, we have to convert these numbers to its equivalent binary first, right? So, equivalent binary of 8 in decimal system. This is already wrote in last 2 or 3 problems. So, we can again write it here. So, to get 8 in binary, you can write it as like this, right? I think you know how to convert this. This in binary system, base is 2. Just like in decimal system, base is 10. The binary system, base is 2. From right to left, we have to increase its power. This position is 2 raised to 0. The second position is 2 raised to 1. The third position is 2 square. The next position is 2 cube, etc. Just like decimal system. The decimal case, we write here 10 raised to 0, 10 raised to 1, 10 square, 10 cube, etc. Similarly, in the binary system, we give its positional value like this. We give positional value like this. 2 raised to 0, 2 raised to 1, 2 square, 2 cube. Okay, so we can easily convert 8 to its equivalent binary because 2 cube is 8. So all other positions goes we want to subtract 5 from 8. For that, we have to find out 2's complement of 5 and add that number to this 8. Okay, so we have to write 5 in its binary form. So using positional value, how can you write 5? 5 means 4 plus 1. So third place and the first place have 1. Okay, so 0, 0, 0, 0, 0, 1, 0, 1. Right? 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are there. This is the first place. There is 1. Second place 0, because if it is here there is 2. We need 2 square 4. So in the third place 1. So 4 plus 1 you get 5. So decimal 5 is equivalent to its binary 5 like this. Now we have to find out its 2's complement. How to write 1's complement? First we want to write 1's complement. 1's complement. 1's complement of this number, just invert these digits. If there is 0, you have to write it 1. If there is 1, you have to write it as 0. Okay, so we can write here just inverting these two, zeros to 1s and 1s to 0s. 1, 1, 1, 1, 1. There are 5 zeros here, so here there is 5 1s. Next one goes to 0. Next 0 goes to 1. Next one goes to 0. Right? Simple procedure. So you get 1's complement of this binary number like this. Now we have to need its 2's complement. Okay? So 2's complement. How to get 2's complement? We have to add plus 1 to this 1's complement. Okay? So 1's complement plus 1. So you have to add 1 here. How to add 1 here? 0, 0, 0, 0, 0, 0, 0, 1. Okay? So I can write here in this side. That means 1, 1, 1, 1, 1, 1. 0, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. This is our 1's complement of 5. Now we want to add to this 1. 0, 0, 0, 0, 0, 0, 0, 1. Okay? In order to add 1, you have to put all other bits are 0. Okay? Now adding these two gives you 0 plus 1. 1, 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0. Okay? There is no extra bit or no lost carry here. You will get result like this. This is what 2's complement of 5. This gives you, this is what 2's complement of 5. Okay, that means if you take 2's complement of 5, it is actually minus 5, right? We already see that. We already found in our earlier problems that not to represent 2's complement form, a negative number, you have to write its positive number first and convert it into 2's complement form. Okay, so 5 in its 2's complement form looks like this. So what is this? This is the binary equivalent of minus 5 in decimal system. Okay, so what we want to do to perform this 8 minus 5, you have to simply add this 8 plus minus 5, right? So we can add here 8 plus minus 5. This gives you 8 minus 5, right? So we can add here 8 is here 0, 0, 0, 0, 1, 0, 0, 0. Okay, this plus binary equivalent of minus 5. 1, 1, 1, 1, 1. 1, 2, 3, 4, 5. 5, 1, 0, 1, 1. Okay. So, you can add these two numbers. 0 plus 1, 1. 0 plus 1, 1. 0 plus 0, 0. 1 plus 1, 0 with carry 1. Then carry goes to here. 0 plus 1 plus 1, 0 with carry 1. 0 plus 1 plus 1, 0 with carry 1. 0 plus 1 plus 1, 0 with carry 1. 0 plus 1 plus 1, 0 with carry 1. Okay, there is a lost carry here. Lost carry. Okay, so this is the result. What's this? This number is equivalent to 1 plus 2, 3. Okay, so binary 0, 0, 0, 0, 0, 0, 1, 1. This is equivalent to decimal 3. So you get the correct result. 8 minus 5, 8 minus 5 equal to 3. You know that result. By converting 8 and 5 to its binary equivalent form, you can find out its result here. But to perform binary subtraction, you have to perform binary addition by finding out the 2's complement of the number being subtracted. Here the number is 5. So you have to find out its 2's complement. 2's complement of 5 is minus 5. That minus 5 is obtained like this. So you have to add minus 5 to 8. This gives you the result like this. So the result is, the equivalent result is this gives you 8 minus 5 gives you 0, 0, 0, 0, 0, 0, 1, 1 with a lost carry. This is the result. Okay, this carry is not in the result to another problem. Here we have to subtract minus 1 from minus 12. So you have to do minus 12 minus 1 in binary form. Subtract binary form of minus 1 from its equivalent minus 12. That is our problem. So what we want to do first? The first thing is we have to represent all of them in its binary form, right? So what is minus 12 in binary form? There is some work done. Why? Because you have to write 12 first in its binary, then take its 2's complement, then only it gives you minus 12, right? So we can do that first. How to write 12 in binary? 12, decimal 12 in binary. How to write? 8 plus 4, 12, right? 8 plus 4. So, fourth and third place. Fourth and third place should be 1. So, we can write here 0, 0, 0, 0. Then comes 1. Then comes 1, 0, 0. Is it correct? Because here 1, 2. Then comes 4. Then 8. 4 plus 8, 12. Okay? All other bits goes to 0. This is binary equivalent of 12. But we need minus 12. How to write it? So we want to take its 1's complement. So 1's complement. One's complement of this 12. How to write one's complement? Invert zeros to 1 and ones to zeros. Okay. So how many zeros are here? 4 zeros. So here 4 ones. Then comes 2 1. So 2 0. Then comes 2 0. That goes to 1. Okay. This is the ones complement of this 12. But we need 2's complement. So 2's complement. How to write 2's complement? 1's complement plus 1. Okay, so we can perform here 1's complement. 1 1 1 1 0 0 1 1 plus 1. So 1 here, all other bits are zeros. Okay. Now we perform the addition. 1 plus 1, 0 with carry 1. 1 plus 1, 0 with carry 1. 0 plus 0 plus 1, 1. 0 plus 0, 0. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. Okay. So here there is no lost carry. This is the 2's complement of this number 12. Okay, so you get here, this is as minus 12 in decimal system. So minus 12 in decimal system is given by 1 1 1 1 0 1 0 0. Okay. Now we have to write 1. But the problem is 1 is the number being subtracted. So what we want to do? We have to perform its 1's complement and want to take its 2's complement. Then we want to add that to minus 12. Okay. So the second step, this is the first step. The second step is converting 1 to its 2's complement. 2's complement. Okay, so in 8-bit notation, 1 is 0 0 0 0 0 0 0 1. 1 2 3 4 5 6 7. 7 zeros as the 7-bit and the last bit, least significant bit is 1. This is 1 in 8-bit notation. Okay, now we want to take its 1's complement. So 1's complement. What is 1's complement? 1 1 1 1 1 1 1 1 2 3 4 5 6 7 0. Right? 1's complement of this number. This 0 1 0 1 0 1 0 1 0 1 0 1 0 1 1 0. Okay, now we want to make it as 2's complement. So again we want to add 1 to this. So you get 1 1 1 1 1 1 1 1. All bits are 1 1 2 3 4 5 6 7 8. All 8 bits are 1. Okay, so this is actually the minus 1, right? 2's complement of 1 is actually minus 1. Now we want to add this to this number, minus 12. Okay, so we have to perform minus 12 plus minus 1. Okay, this is equivalent to minus 1 in decimal system. Okay, so we have to perform this. We can do that here. addition here. So 1 1 1 1 0 1 0 0. That means this is minus 12. So we can add these two numbers, minus 12 plus minus 1 here. Using the binary addition rule, 0 plus 1, 1. 0 plus 1, 1. What about 1 plus 1? 1 plus 1 is 2. In binary it is 1, 0. So 1 plus 1 is 0 with carry 1. Next come here. 0 plus 1, 1. 1 plus carry 1, 0. Again carry 1. 1 plus 1, 0 with carry 1. 1. Again carry 1. 1 plus 1. 0 with carry 1 plus 1. 1. Again carry 1. Goes like this. Finally, you get an extra carry here. Okay. So, this gives our output. We can assume that this should be minus 13. We have to verify that. Is this represent minus 13? How to check this? We have to invert. Actually, this is in its 2's complement form. Okay? So, we can invert this or perform this process. Verify this whether this minus 13 is equivalent. Okay, for that you have to do all these operations. How we convert 12 to minus 12, all these procedures in reverse order. Then you can verify that this is equivalent to minus 13 in the decimal system. So, in this example, we subtract a negative number and a positive number from a negative number. Actually, this is equivalent to adding two negative numbers. That is what happened here. We already write minus 12. Since this 12 is in negative number, we have to represent it using 2's complement form. That is what we have done first. First take 2's complement of 12. It is called minus 12. Then we move on to the number being subtracted. That number is 1. So, we have to take its 2's complement. That means minus 1. By adding minus 12 to minus 1, you get its equivalent minus 13. Okay? So, I think you can do your own ways to these types of binary subtractions.